All right, so we are starting something totally brand new called logarithms. Don't mind the writing that's already there. The video ran out of, or my iPad ran out of video storage, and so it already started writing, so I'm just going to explain what I've got down there. So logarithms are the inverse of the exponential functions that we've been working with for the last couple sections. So what I'm doing right now, or what I had started to do, was to set up a little chart representing y to the 2x. So we're going to start by looking at this function. So I just start to set up a table. We plugged in just like the standard x values from -3 to +3, and we're subbing it into this function right here. So -3, for instance, 2 to the -3rd power. Remember when you have a negative exponent, it flips? So it'll be like the reciprocal, like 1 over whatever that number is. So we have 1 over 2 to the 3rd, which would be 1 over 8. Then the next one, we plug in 2 to the -2nd, so that's the reciprocal of 2 to the 2nd, which would be 1 over 4. And with the -1, we would have 2 to the -1st, which would be 1 over 2 to the 1st, which is 2. So there are our fractions. 0, remember anything raised to the 0 power just comes back as 1. 2 to the 1st, of course, is 2. 2 to the 2nd is 4, and then 2 to the 3rd would be 8. So when we're talking about an inverse function, what we want to do, remember, we switch all of the x and y points. So the inverse would be if we swapped and put x equals 2 to the y. So we would totally trade. All of the x values would become y's, all of the y values would become x's. So we're going to just literally swap those two columns. So 1/8, 1/4, I'm literally just trading all of the x and y columns like this. So there's got to be a function, whoops, this should be 3, sorry. There's got to be a function where I could plug this in and get this out. And what that function is called is a logarithm. So a logarithm is basically like you give me the answer, I'll spit out the power that gave you that answer. Because here with exponential, you plug in a power, the function output would be the answer, like 2 to that power. So logarithm does exactly the opposite. What you give them is the answer that we're expecting, and the output that it gives is the power on 2 that would have given you that answer. Okay, so what we're dealing with is a logarithmic function, the way that it is written. So x equals 2 to the y. We're not really ever going to see it written like that. We write it as y base log of b. Okay, so we write it as log base b of x, and it's literally written as log base b of x. That's the way that you will always see that. So this is a logarithmic function. Okay, so we call y the logarithm of x, which is basically like a missing power. So we're going to define that on this next page here. Okay, so in general, that inverse is x equals b to the x, which we write as, again, y equals log base b of x. Okay, so this thing and this thing are exactly the same. All right, and so we are going to start actually defining what that means. So we've got b and x, so the base has to be a positive. Remember the base cannot be 0. We've talked about that before. I'm sorry, the base can't be 1. So the logarithm of x with base b, we write log base b of x. It's defined as the exponent y that makes b to the y true. Okay, so log base b of x, so if we say y equals, is defined as the power that makes the equation true. Okay, so it's defined as the exponent y that makes b to the y. So I'm going to keep reading that sentence every time that we're looking at one of these examples, all right? So if we put it in 2 words, basically we would say log base b of x equals y, and we're going to write this double arrow, which means this implies this and this implies this. So it implies that b to the y is equal to x. All right, so we can kind of set this apart right here. This is our definition. And so we're going to first use that definition just to translate back and forth. So we call this logarithmic form, we call this exponential form. So in these first two examples, we're just literally going to be translating back and forth between log form and exponential form. All right, so first, this log. So I'm going to rewrite this just so I can start to color code. All right, so I'm going to color code these log and exponential functions. So the base, I'm going to color code in pink. And then this x right here, I'm going to color code that in green. Okay, equals, and then the 2 playing the part of the y, I am going to color code that in purple. All right, so that's currently in logarithmic form. When we put it into exponential form, it goes like this. Base, and then to the y power equals x. So what this is saying right now, logarithm, remember, is an exponent. So we're saying the exponent on 3 that gives us an answer of 9 would be 2. All right, so if we translate it, the base is 3, the exponent is 2, and then we say that that is equal to an answer of 9. So our final answer would be this. We're just putting it into exponential form. Okay, so if we do the same thing with this, your base is 10, the exponent is over here, negative second equals, and then the answer, 1 over 100th. So this way, I think it's easier to go from logarithmic into exponential just because you can look at this statement and say like, oh yeah, that's true. You know that 3 squared is 9. Hopefully we could at least think about the fact that 10 to the negative second would be 100. Remember, this means the reciprocal of 10 to the second. Should be the reciprocal of 100. So that's one way. So that's starting in logarithmic and then ending up in exponential. We're going to go the opposite now. So this is an exponential equation. We're going to write it in log form. So we can write, actually, I'm going to color code again. So 5 is the base, and 3 is the exponent, and then that is set equal to 125. All right, so when I write it in logarithmic form, I start with the word log. So that word it kind of appears when you're going into log form. It disappears when you're back in exponential. So the first number that we're going to write is still the base, but then the other two will trade places. Now here, the y that used to be the exponent is now on the other side. The number that used to be on the other side is now inside my log function. So this 125 is now right here. And then it's set equal to the exponent, which here is 3. Okay, so again, this means the exponent that I raised 5 to in order to get 125 would be an exponent of 3. So I can do the same thing right here. All right, so when I'm writing into log form, I just start with the word log. My base is 27, and then the other two essentially trade places. So the 3 would go right here, and then I set that equal to this 1/3. So this means the exponent that I raised 27 to in order to get 3 is 1/3. All right, so let's use those basic ideas to evaluate some of these expressions. So these, we're going to get enough practice with these that hopefully it'll become pretty quick and easy. So log base 3 of 243 means what exponent would I raise 3 to in order to end up with 243? All right, so we're saying 3 raised to some missing exponent, we don't know what it is supposed to turn out to give us 243. So if we can figure out what that missing exponent is, then we will know what our value of y is. So 3 to what power gives me 243? These we should be able to recognize. If we didn't have them memorized in the previous chapter, it's time to start memorizing some of these powers. And that value would be 5. 3 to the 5th gives me 243. So what that means is that log base 3 of 243 is equal to 5. The exponent that I raised 3 to in order to get 243 is an exponent of 5. Okay, we can do something really similar with this one. My base is 1/2, and I'm raising it to some sort of mystery power in order to end up with 256. Okay, so this one, we're not really familiar with an exponent of 1/2, so we're actually going to employ a slightly different strategy. So you could either do strategy number 1, where you just kind of recognize it, or we're going to do strategy number 2, where we write them both with a common base. So 1/2 is 2 to the negative 1st, and I am going to leave that missing exponent on the outside there. And then 256 is a very, very big power of 2. So let's leave with one that we know. 2 to the 5th is 32. So 2 to the 6th is 64. 2 to the 7th would be 128, and that means that 2 to the 8th would be 256. So I can write this as 2 to the 8th. All right, so remember I can multiply these exponents right here, and now that the bases are the same, I can go back to what I was doing in the previous section. I can say that negative 1y, which is negative y, is equal to 8. So if I divide both sides by a negative 1, that means that y equals negative 8. So that means the exponent that I raise 1/2 to in order to get 256 would be an exponent of negative 8. So just these numbers are really our final answer with problems like this.